We can find normal force indirectly by looking at the other forces that are acting in a system. We can't find normal force directly. It doesn't have its own equation. If we want to find the normal force exerted on a block by the table, we're trying to find a force here. The way that we find forces are by using Newton's laws, so we need to go through the process of force identification, drawing a free body diagram, and setting up Newton's second law equations so we can solve what we've got here. So here I've done force identification. The next thing I'm going to do is draw a free body diagram, which involves setting up my axes, drawing my object as a particle. I've identified that the object is sitting on a tabletop, so the velocity is 0 and the acceleration should be 0. The only force that I have is, the only contact force I have is the normal force from the tabletop. There's no sideways motion, so I don't need to consider friction. And the only long-range force I have here is weight. So now I can set up my equations. I only have vertical forces, so I only need to look at my forces in the y direction. I have normal force that's going up, I have weight that's going down, and my acceleration in the y direction is 0. And so I can see here that my normal force is equal to my weight, which is mg. I do have an equation for weight. And so I can find the normal force. I'm going to finally round that to sig figs. Normal force is a force that's measured in newtons. So here I'm able to apply Newton's laws to find the normal force indirectly, to find the normal force in terms of other forces in the system, in this case the weight of the object. Normal force is important in several different places. We'll see that it has an effect on the force of friction as well. Another way that normal force is important is our perception of our weight, and basically comparing what we feel to what's actually going on. So one way that we see that is the way that scales work. A scale doesn't measure your weight directly. Basically, you step on a scale, your weight pushes down, your scale has to apply a normal force to push up to support you, and the scale reports that normal force as if it's your weight. But think of, for example, if you put a backpack on and stand on a scale, your scale would report a higher weight, even though your weight hasn't changed, because your scale isn't measuring your weight. It would be measuring the normal force that it has to supply to support you, your weight, and your backpack's weight. We call the when we talk about our perception of our weight, we call this the apparent weight. And that is the weight that we feel. If we are just sitting on a horizontal surface, our normal force is our apparent weight, and our normal force is just equal in magnitude to our actual weight. So if we're just sitting still and nothing's happening, our apparent weight is our weight, which is why scales work most of the time. But sometimes we feel heavier or we feel lighter. That doesn't mean that our weight has actually changed, right? We said that our weight is mg, which hasn't changed. So our weight hasn't changed, but we feel heavier or we feel lighter. We can see here how that can happen. So let's imagine a situation where we've got a person in an elevator that is accelerating upwards with a magnitude of a. So here we have a person, they're in an elevator, and we're told that the elevator has an upwards acceleration a, and we want to understand what this person is experiencing. So again, we will follow the rules of force identification. In this case, there's normal force from his feet supporting his weight, and then there's his weight as he moves upwards. After we've done force identification, we draw a free body diagram. In this case, the weight is going up, the normal force is going down, and we know that this person is moving upwards and their acceleration is upwards. So notice that I've drawn the weight a little bit bigger, the normal force a little bit smaller, because they are moving upwards. And actually I have those backwards, don't I? Their normal force is a little bit bigger because it's pointing upwards. Their weight is a little smaller because we have to have a net upwards force to give us that acceleration. And you can see from there kind of where we're going. We only have forces in the y direction. Our forces in the y direction are our normal force that's going up, our weight that's going down. Those are the only two forces, so we've accounted for them. Our acceleration has a magnitude of a, and that acceleration is upwards as well. And then what we can do here is solve for the normal force. Because we just said that the normal force is the apparent weight, it's what this person would feel. and what this person feels in their feet and pushing up through their legs. And that's how you interpret or experience your own apparent weight. Their apparent weight is his full weight plus this extra term that accounts for the acceleration of his body upwards as it accelerates upwards with the elevator car. So his actual weight is going to be his regular weight plus some extra, so it's bigger than it usually is. And thus this person is going to feel heavier while they're accelerating upwards in the elevator. Basically, their apparent weight is going to be greater than their actual weight, and so this person is going to feel heavier. If you had the same situation where the person was accelerating downwards instead, that change would change our free body diagram. We could be accelerating downwards, even if we're moving upwards or downwards, that doesn't matter. It would change the lengths of our vectors here. The magnitude of the acceleration would be the same. We have the same acceleration. This plus sign was saying that we were accelerating upwards. If we're saying that we're accelerating downwards now, all we would have to do is change that so we have the same magnitude but the opposite direction. With a negative sign here, that would give us a negative sign here. Now the apparent weight would be the true weight minus this term. So if you take a value and subtract something, you're making that value smaller, meaning the apparent weight would now be smaller than the actual weight. And now in this case, this person would feel lighter if they are accelerating downwards. One way you could think of that is that if you're accelerating downwards, you're quote unquote using up some of gravity to accelerate you downwards. And so that is less weight that your body has to support. And so you feel lighter as you're accelerating downward. You'd feel heavier as you accelerate upwards. We just said that we could represent the apparent weight as being the weight plus mass times acceleration. When this was a positive term, when we're accelerating upwards, we felt heavier. When this is a negative term, because we're accelerating downwards, we felt lighter. If we are in free fall, that's a special case. In free fall, our acceleration is negative g. So what happens in that case is we have mg from our weight plus m times negative g from the acceleration. And so these two terms cancel each other out, and our apparent weight in that case is 0. So then we are weightless. I put weightless in quotation marks there because you're not really weightless. Your weight is still there. You're still close to the earth. So the earth is still pulling on you, but you feel weightless. Your apparent weight is 0 because you're accelerating downwards at that free fall acceleration. So you don't feel any normal force. You feel like you're floating, but you are still falling due to the Earth's pull on you. Tension is another force that doesn't have a equation for it. It is a reactive force that's going to respond to other forces acting in the system. We can find tension similarly to how we found weight before. In this case, we have a block of mass 1.4 kilograms is suspended by a rope. We want to find the tension. Tension is a type of force. The way that we find forces is by applying Newton's laws. The way that we apply Newton's laws is by doing force identification, making a free body diagram, and coming up with Newton's second law equations that we can then solve. So step 1 is to draw a picture. Step 2 is to do force identification. Step 3 is to draw a free body diagram. And step 4 is to take our free body diagram and use that to find a Newton's second law equation. And so in this case here, we can see that our tension is the weight, which is mg. And we can round to sig figs and get our overall tension. Tension is a force. That force is measured in newtons. Also notice here, T is the magnitude of the tension. The magnitude of the tension is 14 newtons. We've already accounted for the direction of the tension. We know that the tension in the rope always pulls towards the center of the rope. The tension in the rope is pulling the block up. The tension in the rope is pulling down on the anchor in the ceiling. It's pulling both ends of the rope towards the middle of the rope. So we do know the direction of the tension. Tension is technically a vector, but we found the magnitude of the tension here. We can put all of this together as well. with tension and normal force in the same situation, but the only way that we can find tension or normal force is either by finding it in terms of other quantities, which we've done earlier in this lesson for normal force and tension separately, or we can measure the normal force or the tension directly. In this case, we have a spring scale that we can use to measure the tension in a rope, or we could use a regular scale to measure the normal force pushing up on the bottom of an object. We can use those values to measure those quantities directly and then use those to calculate something else. In this case, we want to find the normal force supplied by the tabletop. We're trying to find a force in terms of a mass, which is related to weight, and in terms of tension. So if we want to find a force in terms of other forces, that means that we need to be using Newton's laws. We know how to do that. We're going to use force identification. Then we draw the free body diagram, and then we use the free body diagram to set up Newton's second law equations. So in this case, all of our forces are in the y direction. We have normal force pushing up on the bottom of the block. We have tension pushing up on the bottom of the block. We have weight pulling down, and the block is sitting on a tabletop. So the acceleration in that case is going to be 0. And so again, what we do here, we don't have equations for either. We have our Newton's second law equation. Then we can start simplifying what we've got. Our normal force is unknown. We have tension. Our weight we can represent as the equation for weight. Now we know what tension is. We know what these quantities are. We can use those to find the normal force. And again, normal force is a force, so it's measured in newtons. This is the magnitude of the normal force. We've accounted for the direction already. So this is how we can apply Newton's second laws, our force identification process, to find various quantities.